faster. Okay, so if you open that 4.4, so you have it here, and then you open 4.5, it's also the same. Okay, so by the time we move on that, I'm going to upload the material that you need. And also, hindi ko pa ito na-propose, but I think we're going to utilize until, I think, what's the last day? December, is it December 20? And
December
then
21, May.
December 21. And then we're going to have your final exam on that January thing. I think January 5 to 11, kung ano man yung schedule na mangyayari. So the way we're going to do, just to make up, okay? So we're going to meet synchronously, and I'm going to make all the materials of recorded video also asynchronously. So everything will be up to date. Now, it's up to you if you want the quiz to be per module or every week. We decided the problem set to be per module, but for the quizzes, we are not allowed to give any quizzes this week. So we're giving you the chance to decide anong gusto niyo sa quiz, every week or every module. I think we will ask everyone. I mean, kahit yung mga wala dito. You don't have any quiz this week until next week, which is November 16. Because there's a memo that went out that we're not allowed to set any deadline to you. Okay, that's the reason why I didn't post the video yet, so that you will have the wellness thing. And I just decided that we do the introduction synchronously, and then the rest will be asynchronous. And then maybe next meeting, yung calculations, we're going to go over them. So this is the tentative deadline. I have not posted this yet, but I'm going to post it in both sections. So spectroscopic method, maybe for the next 2 weeks. And then the mass spec, okay? And then we have the electroanalytical, and then some miscellaneous techniques. Now, the problem here is there might be some coverage that I will be more specific because of my specialty. Like here, they didn't put one aspect there, okay? There should be vibrational spectroscopy there. That's the Raman and the IR. So some mass spec, maybe we'll just go a little bit basic, okay? And then electroanalytical, we can go the 3 common one. And I'm not sure if we're going to be able to discuss most of these miscellaneous techniques. So ito yung parang study guide natin for the whole semester, yung course guide. So we are now in module 4. So we might have the introduction today, okay? And then the rest will be video, recorded video. And then we will also meet next meeting. So we might meet every meeting from now on. But it will going to be recorded just in case hindi kaya nung iba na mag-meet every meeting. So questions so far? So I think we can start. We're already 21. So that means 19 of you are here. Almost close to 50%. So as usual, I'm just going to use the IC material. Okay. So the introduction that we have for spectroscopy is the principle behind spectroscopy. So when we're talking about spectroscopy, it's some sort of the interaction. Okay, so this is how matter interacts with light. So yun yung we could say nature or the main principle behind spectroscopy, the interaction of light with matter. And of course, you know, light is what? An energy. Okay, so that means some or more, some if not most of these methods that we use in spectroscopy deals with energy. Okay, so spectroscopy, that's the general term for the science that deals with the interaction of various types of radiation with matter, and that radiation, that's light. Okay, so it may include the interaction of electrons, ions, and acoustic waves. So meron tayong level na tinatawag na atomic at molecular. Okay, so spectroscopy, that's the general term for the science of the interactions of light with matter. Now, if you're going to put some sort of measurement, okay, to this interaction, ang nagiging term na doon is spectrometry or spectrometric method. So those are the two general terms that they usually interchangeably use in this course. But if you're going to look in detail, the formal definition of them, they are really what we call different. One is just the interaction of light with matter, while the other one is a measurement. So they're trying to put some sort of analysis doon sa interaction na nangyayari. Okay, so spectrometry or spectrometric methods are referred to the measurements of the intensity of radiation with a photoelectric transducer or other electronic device. So since we are talking about light here, so I think you have to go back to a lecture that you have. I don't know what chem is it now, but during the time I'm teaching there, we have this Chem 17, which is General Chemistry 2. So we discussed there about the so-called electromagnetic radiation or light. I don't know if you still able to get the course Chem 17. Nakapag Chem 17 pa ba kayo? Or iba na yung term na ginagamit ngayon? Oh, Chem 18 na. Oh, Chem 18 na siya. Oh, I see. So sorry for the numbering, but all I know is Chem 17 during the time that I was teaching there. So the way that they look at this electromagnetic radiation is the so-called nature of light. Okay, so since before, they always associated light as having wave property. So kapag meron kang wave property, so that means you have some sort of a pattern like that one. Okay, so the way that you do it is it's going to be described by usually the wavelength and the frequency. So usually that's the one that describes a wave. Okay, so if you have a wave property of radiation or light, it's demonstrated by sinusoidal wave model, shows characteristics such as wavelength, frequency, velocity, and amplitude. And unlike the other wave phenomena, electromagnetic radiations can be transmitted through vacuum because it does not require a supporting medium. Now, if you have this so-called wave model, it cannot associate itself with absorption and emission. And unfortunately, this absorption and emission, that's the mode of light interaction with matter that is being described in spectroscopy. So the wave model cannot explain it. So you have to explain it in terms of the so-called particulate model or particle model. So dyan na yung pumapasok. I don't know if you still remember this one, the dual nature of light. Okay. So the way that they look at this particle model, they refer to light as something that is discrete, not continuous. Okay. And this particle model would explain the phenomena by viewing the electromagnetic radiation as a stream of discrete energies that can be called photons or quanta. Okay. So if we're going to look at the nature of light that they have before, so the one that is accepted during that time is light is a wave. And usually, if you're going to look at the electromagnetic radiation, there's two fields that you have there. The electric field, okay, and the magnetic field. That's why they call it an electromagnetic radiation. It's a combination of these two. Okay, and as of now, they can still use this what we call two field that we have, electric field and magnetic field, especially in one of the spectroscopic method known as NMR. Okay, they still use this principle that they have. And if you have this wave model, so these are the properties that usually describes a wave. But the two most important thing that I usually taught my students in Gen Chem is usually a wave can be described in terms of the wavelength. So that's the length between two successive wave. So it's either the peak or the what we call the trough. And then we also have the so-called frequency. So this is the number of cycles or oscillations per second. Okay. Now, other term that they use is the so-called amplitude, which is just the height of the wave's electric vector, and the so-called wave number. And wave number is just per centimeter. And you can describe it as just 1 over the wavelength. So usually you use it when you go to Raman, okay, spectroscopy. So this is how you describe the so-called wave model. And there's still another term that they utilize here to describe this wave model. You also have the so-called velocity of propagation, which is just the nature, the rate of travel through space, which is dependent on the composition of the medium. And the constant that we need to know, okay, when we're talking about light is what we call the speed of light. Because if you're going to remember your Gen Chem, the speed of light is just equals to what? The frequency. So the speed of light is just equals to the wavelength times the frequency. Okay. And I don't know if you recall, are you still familiar with this equation? The energy is equals to Planck constant times the frequency. And if you're going to relate energy with wavelength, all you need to do is rearrange this one. So you're going to have this expressed as Planck constant times the speed of light over the frequency. And as you could see here, the relationship that you have between energy and the wavelength, the shorter the wavelength, the higher is the energy. The longer the wavelength, the lower is the energy. Okay. So that's this what we call equation here revolutionize the concept of light as being what we call matter. And it all started with Planck explanation of the so-called black body radiation, wherein he explained that the phenomena of black body radiation cannot be interpreted using the wave nature of light. Okay, it can be only be interpreted if you use light as a particle. Okay. And as we go on here, the particle model, okay, what they have here in this model is they view light as a discrete particle, and usually they call it the photons. And even Albert Einstein adopted the concept by Max Planck of having light as a particle. And with this, what we call model, they can view light as being scattered or counted, or the term that they use is quantized. Okay. And if you have that, what we call model or view of the light, so you could see there that an atom, okay, can be excited by absorbing light at a certain energy level. So energy required a photon to give this transition. So as you could see here, it is what we call at a particular energy. And with this, they end up with the energy of wave particle. And this is the one that I have shown to you. So this is one of the revolutionary equation proposed by Max Planck. And it's really very important that you have to view light as a model for some or most of these spectroscopic method to be possible. Okay. So if you're going to look at the definition that you have here, so this is the energy, H is the Planck constant, which is 6.63 times 10 to the negative 34. And then B is mu is equals to the frequency, lambda is the wavelength. Okay. And here, when you're going to replace that one, HC or B here, that is equals to the wave number. And if you're going to look at this, energy is proportional to frequency, and wave number, energy is inversely proportional to wavelength. I think one main contribution of light being a particle is the so-called photoelectric effect. Okay. So the photoelectric effect, this is the phenomena where electrons are ejected from the metal surface after absorbing a certain amount of energy. Okay, so this was discovered by Hertz, of which the unit of the frequency is named after. Okay, but he was not able to explain it. So numerous experiments involving the photoelectric effect followed using the so-called vacuum phototube. And the only one who was able to explain it is Albert Einstein. And in Albert Einstein explanation, he had to borrow Max Planck concept of light, that is being a particle. Okay, so he provided the theoretical explanation, and I don't know if you knew it. That's the basis for him winning the Nobel Prize. Although Einstein is known for the theory of relativity, but the Nobel Prize that he won is for the explanation of the photoelectric effect. And Millikan in 1916 confirmed, okay, with systematic studies, Einstein theoretical explanation, and all of these supported the particle model of for what we call radiation. So that's the essence that you have here in spectroscopy. So if they were not able to explain the dual nature of light, most of the spectroscopic method is not possible. I don't know how you view or how you understand the dual nature of light during your Chem 18. But usually I always tell my student, come to think of this dual nature of light as if you go to a beach. So from far away, you see just a coastline. So that's, we could say, a continuous one. But if you go into details, that coastline is made up of what? Sun, which is usually a particle in nature. So I think that's the best description of the so-called dual nature of light. And if you want to know more about this photoelectric effect, so there is some tutorial materials that you have here. I'm not sure if it's still possible because I think they phased out the Adobe Flash. Okay. Now, if we're going to expand what we have discussed, so usually every spectroscopic methods, they are in this spectrum of this electromagnetic radiation. And if you're going to look at this, you can do it in terms of what we call the length, okay, or the frequency. So this side, we could say this is the longer wavelength, okay, and the lower frequency. And in addition, this is also the one that has the lower energy. So if you move further here, so you have shorter wavelength, and that also means higher frequency and higher energy. So if you're going to look at, okay, the one that allows us to see the different color is really a very small region, the visible right. Okay, it's only a small fraction between 350 to 750 nanometer. So I don't know if you're still familiar. Okay, are you still familiar with Roy G. Bibb? I have to use this one so I can at least. Familiar pa kayo dito? So which one is the longest wavelength and which one is the shortest wavelength? How did you understand that during your time? So usually this is the shortest wavelength and this one is the longest wavelength. And in terms of energy, what can you say about this side here and this side? So this is the one that has the highest energy. And this is the one that has the lowest energy. That's why they said if you tan yourself under the sunlight, you get burned because of the high energy that you have there. And if you have the so-called ultraviolet, usually it's more energetic, okay, compared to the other one. And you can also say that this is the one that has the higher frequency compared to the one that you have on this side. So this is just really a review of what you have learned. Okay. Now, if you're going to look at the different radiation type that you have here, so you have here the radio, the microwave, the infrared, the visible region, the ultraviolet, the X-ray, and the gamma rays. Now, if you're going to look at this, some of these are already the spectroscopic method that you use. Okay. They have the so-called microwave spectroscopy. They have the infrared, they have the visible, and then you have this what we call ultraviolet. In fact, the one that we're going to focus is the so-called UVBs. Okay, so UVBs is just the term for ultraviolet visible region. That's the main, we could say, focus of spectroscopy. And all you need to do is, all you need to have is the so-called spectronic 20. I'm not sure if you're familiar with the so-called spectronic 20. Okay, that's the simplest spectrometer that you can use. And if you're going to relate the different radiation type that they have, you could say that from left to right, the energy increases. Okay, especially what we call the X-ray. It's more powerful compared to the UV. And the UV is more powerful than the visible region, which is more powerful than the infrared. Okay, and if you're going to look at the different spectroscopic method, you could see the type of the transition that they have. So if you're going to look from here, you could say this is what? from the highest energy to the lowest energy. So that's the one that you have in this table. Okay. So if you have this gamma ray emission, so the wavelength that it has is so short. So that means it's really highly energetic, 0.005 to 1.4 angstrom. And the type of transition that you have there is a nuclear transition. And then you can also have the so-called X-ray absorption, emission, fluorescence, and diffraction. Okay. And the type of transition that they have is inner electron. So there is a method called X-ray absorption or X-ray emission, or the so-called XRF. And usually the method that this utilize is for metal detection. We have an X-ray diffractometer. So that is the one to use to determine the crystal structure. Okay. So the type of transition that you have there is the inner electron. And then you can also have the so-called vacuum ultraviolet absorption. Okay. And it ranges from 10 to 180 nanometers. So it involves bonding electron. And then the most common one, you have the absorption, ultraviolet absorption. You can also have the ultraviolet emission and fluorescence. Okay. So usually when you say absorption, that's just the absorbance, the UVB absorbance, and that's the most common spectroscopic method. Fluorescence is just applicable if your material fluoresces. Okay, so it involves absorption where the electron is excited or to go from the ground state to a much higher state, which is the excited state. And upon going back to the ground state, it passed through some transition, emitting some energy. Okay. So it involves this what we call electron. So when electron is involved, usually that means they are highly energetic. Okay. Now, on the other hand, the IR and the Raman, it's mostly vibrational. So what it do, it's not going to break bonds. Okay. It's just going to force your what we call molecules to vibrate. IR would be absorption, Raman would be scattering. Okay. And usually it's used to determine the functional group of a given molecule. And then you also have microwave absorption. And again, this is not as energetic as UVBs. So it just rotate your what we call molecules. And then you have this electron spin resonance and the NMR. So both of them involves the spin of electrons in the magnetic field. Now, if you want to determine the exact structure of a given compound, usually they use the so-called NMR. Okay. So these are, we could say, the common spectroscopic methods based on the electromagnetic radiation. And usually we can use these so-called classes or classification of these spectrochemical methods. So here in this portion, we already base them on the measurement. You can classify one as emission. So this is just something to do with the emitted power. So you measure here, okay, the emission that have, and this type of method would include the atomic emission. So you can use here the AAS. And then you have also the luminescence. So in the luminescence here, you also look at the radiant power that is measured, the luminescence. So this is the one that undergo phosphorescence and fluorescence. Okay, so chemoluminescence is due to chemical, bioluminescence is due to some biological factors that can happen. And the type of method that you have here is the atomic and molecular fluorescence, the phosphorescence, and chemiluminescence. Now, we can also have this so-called scattering. Okay, so this is not as powerful as the other one. So it looks as the scattered power. Okay, and this is the basis of Raman, and then turbidity and nephelometry. But the most common that we have is the so-called absorption, and it can be atomic and molecular in nature. So when we're talking about atomic absorption, we're talking about AAS, and usually it's basically used to determine the concentration of some metals. Now, when we're talking about molecular absorption, you just look at the transition of the electrons in a given compound or atom. So those are, we could say, the different classes of spectrochemical methods. So this is the basis that they have on how to use spectroscopic method as usually as a quantitative method of analysis. Okay, if I'm not mistaken, the qualitative method of analysis here has just something to do only with the vibrational spectroscopy, but the rest usually you use it for quantitative method. So questions so far? Anyone has experience in these methods? Have you used Spectronic 20 before the pandemic? One of the video that I will ask you to watch is the experience that I have in this different spectroscopic method. So I have experience with UVBs, fluorescence, both the steady state and the lifetime, and then the vibrational spectroscopy, IR, and what we call Raman. And then I also have a little experience with circular dichroism. So it's something to do with optical activity. Okay, and it's also under we could say spectroscopic method, but I think it's not included in the discussion that we have here. Okay, so questions so far before we go with the UVBs? So after I think the balance and the pH meter, a chemistry laboratory should have at least a spectronic 20. So if you have a spectronic 20, you can do a lot of quantitative analysis. Okay, and spectronic 20 would fall on the so-called UV visible absorption spectroscopy. So this is the one in the range from 180 to 1100. But if you're going to look at the visible region, usually it's around 750. Okay, so the way that they look at this one is the colored that are formed if you react your sample, let's say with a certain chemical. Okay, and then usually the intensity of the color is directly proportional to the concentration of the chemical. Okay, now UVBs is not useful in giving structural information, but it's very useful in quantitative measurements. That's why I told you sometimes they said after the balance, the most important instrument that you need in a chemistry lab is one that is UVB spectrometer or spectronic 20, because using that, okay, you can be able to do quantitative analysis. So the way that they do this quantitative analysis here is the concentration of the analyte can be determined by measuring the absorbance at some wavelength and applying the Beer-Lambert law or the Beer's law, as some of the book would say. Okay, so this is the instrument that includes color comparators, basic colorimetric devices, and automated spectrometer. So if your sample can form a color, most likely you can determine it quantitatively. Okay, just to let you know, the basis of all instrumentation, if you want to determine its concentration, is just to run a calibration curve that contains different concentration of the standards. And all you need to do is make a calibration curve, different concentration of your standard solution and the respective signal. And all you need to do is you have your sample, get the signal of your sample, and then get the corresponding concentration using the calibration curve. That's usually the SOP that you have in instrumental analysis. That's why, I don't know, for me, that's the easiest way to do it. Okay, if you do research, whatever the results, that's it. Unlike in organic chemistry, you have to synthesize, and if you were not able to synthesize because there's a lot of side reactions, so that would be a little bit more challenging. So the only challenge that you have in analytical chemistry is if you're analyzing, let's say, complex sample, complicated sample. So what are the other components in your sample? What will be its effect to the analyte that you are analyzing? Okay, because in the UV-based analysis, they can interfere, okay, with the analysis that you have. So that's the challenge that you have to develop a method. And the good thing about these UV-based, they are usually used as detector in liquid chromatography and capillary electrophoresis. If you recall our lecture on chromatography, so that is one of the detector, and usually it is non-destructive detector. So you can tandem this detector with other detector. So my experience, I use UV-based and then maybe some nuclear base or radionuclide detector, and then the mass spec. So the mass, when the sample reach the mass spec, it will be destroyed. Okay, but before it's being destroyed by the mass spec detector, it can already pass through a UV-based detector and a radionuclide detector if your sample is radioactive. Now, where is this UV-based useful? Okay, so usually you can use this to characterize some of the sample, because what happened when you have this UV-based, there's usually the electronic transitions of these organic compounds. So when a molecule absorbs a photon, so this is when they absorb an energy from the UV-based region, the energy is captured by the outermost electron. So usually if it's really in the visible region, it's highly energetic, okay? And the tendency that they have is your outermost electron can be excited, okay, from the ground state to a much higher state, or a state of a higher energy level. So they found their use in analyzing this so-called organic compound, okay, in atoms such as hydrogen, carbon, nitrogen, and oxygen. The observed transition in UV-based spectrometry involved in sigma, pi, or non-bonding and molecular orbitals. Do you still remember this in your Gen Chem? What theory is this? Anyone? What have you remember about this one? Usually this is the MOT, right? So the bonding and the anti-bonding, the sigma star thing, okay? So if you're going to what we call apply this molecular orbital theory, that's the one that they use to describe the electronic transition of the organic compound. Okay, so the transition that you can have there could be from sigma to sigma star, or from bonding to anti-bonding. So it can also be from pi to pi star, like the one that you have here, or you can have here what, a non-bonding to anti-bonding, or a non-bonding to pi star. So what do you need for this to happen? What do you need for this transition to happen? Anyone? What do you need? Anong kailangan nyo para at least yung electron dito mag-move papunta doon? You need energy. Yan yung in the form ng tinatawag na UBPs, energy. And if you're going to look at each of these transition, usually parang ano yan signature transition. Okay? I'm not sure if you have a discussion on this 140. Are you taking Chem 140? 140 pa ba yun, yung organic analysis? They also utilize instrumentation there. Okay? So if you're going to look at the transition that you have here, so meron tayo itong sigma to sigma star transition. So this is a promotion of an electron from a sigma bonding molecular orbital to a sigma anti-bonding molecular orbital. And if you're going to look at this, ang taas ng energy nila. Right? So it really requires a significant amount of energy. And this is only possible in far UV. Why? Okay. Far UV is more energetic. Okay. And this is the reason why yung tinatawag na saturated hydrocarbons absorb at the near UV. What is the saturated hydrocarbons? Are they the one that has a double or triple bond, or the one that has just single bond? Inire-review ko lang kayo sa organic nyo. So if you have the saturated hydrocarbon, that's just the one that has a single bond. And they usually absorb in near UV, like what we call the hexane. So yung alpha lambda max ng hexane is around 135 nanometer, and this is still below the UV region. Okay, so yan yung sigma to sigma star transition. So that's the one that has the highest amount of energy if ever lumabas to sa multiple choice question. Okay, and then you also have the N to sigma star transition. So in oxygen, nitrogen, sulfur, and chlorine atoms, these are the non-bonding the electrons. So these electrons can be promoted to the sigma star molecular orbital, or the sigma anti-bonding molecular orbital. And if you're going to look at this transition, this is not as high as the sigma to sigma star. So if you're going to look at the previous slides there, this is just where, okay, from N to the anti-bonding. So this one. And if you're going to look at this transition, this requires moderate intensity located at 180 nanometer for the alcohol, 190 for the ethers and the halogen derivatives, and 220 for the amines. Okay, so alcohol is the O, ethers is also O, halogen derivative, which is chlorine, and the amines is nitrogen. Yep. And then we also have the N to pi star transition. So if we're going to look at this, this is just this one. So in terms of energy, we could say it's lower than the N to sigma star. So it requires a low intensity. And it's observed in molecule containing a heteroatom carrying lone pair. So ano yung mga heteroatom carrying lone pair? Anyone? So if you have this hetero lone pair, so usually you have N, you have O, ano pa? Is S one of them also? So these are the one that contains the lone pairs. And the one that is really affected here, we could say, is the carbonyl bond. Because if you look at the carbonyl bond, di ba, paano ba yung carbonyl? C double bond O. Is it like that? And meron kang lone pair doon. So this is just some sort of a review that you have in your Orgo, because this topic that we have here is really discussed in organic chemistry. Okay. And then we have the phi to phi star transition. So these are compounds containing isolated double bonds, and it shows a strong absorption at 170. So if you're going to look at pi to pi compared to N to pi star, so I'm just trying to show you here. So mas malaki yung energy na kailangan dito compared to N to pi star. And that's the reason why this is at 170 nanometer compared to the one here, which is 270 to 295. So this is more energetic, 170 nanometer compared to 270 to 295. And if you're going to look at the absorption characteristic for some organic chromophores, so you could see them here. So you have here the alkene or the alkene, okay? Like heptane here is 177, then you have a conjugated alkene. So these are the unsaturated thing, 217. And then you have heptane, okay? And then you have the carbonyl. So if you're going to look at this, okay, their lambda max depends on the functional group that they have here. Now, all of them are, we could say, the heteroatom type. Okay. So question, before we go on the instrumentation. So if we're going to look at the instrumentation in the UVBs, I think ito yung common na makikita mo, hindi lang sa UVBs, but in most spectroscopic method. Okay? All spectroscopic methods, they always have the light source. Why? Bakit? Anyone? Why do you think the light source is needed? So if you're going to look at that definition that we have there, okay, in terms of this spectroscopy, this is just the interaction of light with matter. So without the light source, there will be no interaction with matter. So the light source is the source of your electromagnetic radiation. Okay, and then you can have the so-called wavelength selector. So wavelength selector is just narrowing the light source that you have to a certain wavelength. Another term that they usually use for wavelength selector is your monochromator. Okay, so once you have the light source, you pass through it in this wavelength selector, or sometimes your light source is even what we call a specific wavelength light source, not the broadband type. But if it's a broadband type, you need the wavelength selector. So it will just going to use the energy or light source at that particular wavelength. And what happened, once you have the wavelength selector, it's going to radiate your sample cell. So that's where you put your sample. Okay. So once it passed through your sample, You can determine the transmission, the absorbance, the scattering, and all of them will be monitored by a detector. Okay, and for you to be able to interpret the results that you have, that detector is tied up to a readout system. So I would say if we're going to look at the UVB spectrometer in the next slides, next following slides, all of them has these parts in their instrumentation. So you have a single beam spectrometer. So this is the light source. And then it will pass through a filter or a monochromator. So that's your wavelength selector. Okay. So what you're going to do, you can use a shutter there. Okay. And then it passes through your sample cell. So your sample cell can have a reference electrode or just a sample cell. Okay. So usually in a single beam, it just passes through what we call the reference cell that you have. And then the photodetector, that is your detector. Now, in the readout system, since the detection or the signal that you get is really small, there's an amplifier, okay, to make your signal much more, we could say, sensitive and transmitted to the readout system. So this is like a spectronic 20, what do you call this, block diagram. So here you could say radiation from the filter monochromator passes through either the reference cell or the sample cell before striking the photodetector. So it's just either here. Now, if it passes through both of them, that is a double beam. Okay, so the difference of the double beam and the single beam. So what will happen? Both, okay, the selected light passes through the reference cell and the sample cell. And there's two detectors that you have there. So what they do is they just look at the difference in the signal that they have. So the difference is usually due to the sample that you have. Okay, and then from the photodetector, again, an amplifier is there, and then you have a readout system. Now, they always ask, where do you think you can improve a spectrophotometer? What part do you think can be improved in your spectrophotometer? So tingin nyo, alin yung pwedeng i-improve pa to at least enhance the signal and improve the analysis? Anyone?
Mag-add po ng amplifier.
Ano yun, Teres?
Amplifier po.
Sa amplifier? So sa tingin nyo, I mean, if you are the one who will ask, how can you still improve the analysis using a particular instrument? Or what part do you think can still improve that will enhance the signal? So usually they said mostly it's here in the detector. Now other school of thought says could be the source. But the problem is, they said, if the power of the source is too powerful, it might destroy your sample. Okay. So the way that they try to do is maybe the one that will generate higher signal will increase the analysis, or will improve the analysis that you have. That's also the question that they have in chromatography. Which part of chromatography that you can modify to improve the analysis? So they said the pump, what they do is use a higher pump. They said it's the column, changing the size of the material in the column. But if you make it smaller, you're going to need high pressure, okay, to push your sample and the solvent to pass through the column. Kaya meron silang tinatawag na ultra high pressure liquid chromatography. So those are the things, because I think from the time that I use this one, I'm not sure if the Perkin-Elmer is still there in ASL, okay, until the one that I'm using right now. And I always laugh because even here at PACE, we have the same Perkin-Elmer that I use there in UPLB. And I always tell my students, we have to use this before you're going to use the more high-tech one. And they always complain because it takes a while for them to get the signal, and then they have to save it in this what we call diskette, the floppy disk, the 3.5 inches floppy disk that they have. Okay. Now you can do qualitative analysis in what we call UBBs. And the signal that you obtain from the absorbance usually is affected by the nature of the sample. So usually if you have a solvent, it can have a direct effect on the signal that you have. So you can get an absorbance wherein you just have the vapor. And if you do that, you're going to have a sharp peak. Peak similar to what we call GCMS or LCMS. But if you have some solvent with it, well, it depends. If you have non-polar solvent, what will happen is it's a little bit broad compared to just the vapor. But if you have polar solvents, what happens is it's broaden out the peaks and then eliminates this what we call structure. So you could say the solvent can affect the position and shape of the curve. So here the example that we have is 1, 2, 4, 5 tetrasin in different medium. So if you're going to look at the structure there, this is just what? Okay, a 6 cyclo. It's not a 6 carbon because 4 of them is made up of nitrogen and then you have a carbon. It's just like a benzene, but you replace, I don't know if you could see the structure. You replace 4 of the carbons with nitrogen. And if you're going to look at this, this is the signal that they have. And the experience that I have with what we call my students, so they measure benzene. So I asked them to add a drop of benzene in a cuvette and then let it equilibrate for 5 minutes and then get this what we call the absorbance, and they will really show sharp peaks compared if you have the liquid benzene. Okay. And there are terms that we can utilize here. So we have the bathochromic shift, and then we have the hypsochromic shift. So the simple term that we have here, what do you call this in terms of color? Red shift, blue shift.
Red shift.
Okay, so since it goes to longer wavelength, the bathochromic shift is the red shift. And then the hypsochromic shift is the blue shift. So that's the term that they use. Because experience told me that if you want to analyze a certain compound, usually, depending on the polarity of the solvent, it can undergo red shift or blue shift. The peak, the lambda max, can move to the red region or to the more blue region. So the term that they have is bathochromic shift and hypsochromic shift. So if you're going to look at this, shift to longer wavelength and shift to the shorter wavelength. Now, if the absorbance increases, we could say that's a hyperchromic shift. If the absorbance decreases, that's the hypochromic shift. So these are just terms that they use, and I hope you're going to be familiar with them. So these changes come as a result of the structure of the entire molecule or as a result of the interaction between the solute molecules and the solvent molecule. So usually there is a term, they call it the solvachromic study or solvatochromic study. So what they do is they just try to determine what will be the absorbance of, let's say, a certain chemical at different solvent of different polarity. So sometimes they will see it like this. So maybe the more polar goes there or the non-polar goes there. So we could say more polar here, and then you have non-polar here. Okay, so it's a very good study, especially if you have some chemicals that you don't know the property. So experience that I have is, I'm not sure if you're familiar with these ionic liquids. So you seldom see an ion compound in liquid form, right? So usually if you have an ionic compound, what's the state that you have? Okay, all salts are usually what? Solid. But if you have ionic liquids, these are ionic compounds in liquid form. So they don't know the property that they have. So what we do, okay, we look at a certain ionic liquid and we put it at different solvent, and then we run the ionic liquid as it is at its own, and it gives us an idea, okay, on the nature of the ionic liquids. Okay, will putting it in a more polar solvent makes it blue shift or force it to shift to the blue region or shift to the red region. But what we observe, whenever we put it in a solution, it peaks broaden compared to it's just as it's it. So that's the information that you can get from these so-called UVBs. They're really, we could say, useful. Okay. Now, maybe you can watch the video that you have here, UVB spectrometry and how to operate. And then there's also a page there in LibreText showing you how it's being utilized in organic chemistry. As I told you, I'm sure 140 covers it. I don't have 140 because I'm a BS Ag Chem. It's required only in chemistry major. So unfortunately for me, I was not able to take 140, but I have housemates before who are chemistry major and they have this 140 course. And I think you still use the book by Schreiner about organic analysis. So I think that's the Bible that you have in organic analysis. Okay, so if we're going to look at the history of this method, it really goes a long way. Okay, so it goes when Pierre Bouguer postulated that if a given width of a colored glass absorbs half of the light, assuming from a source, then a double width will reduce the light to a quarter of its initial value. So this is just when they observed that if you pass color through glasses, they observed that some of these light are absorbed by these what we call colored glasses. So that's, I think, the start of using devices to measure the interaction of light with matter. Okay, so it has something to do everything with colorimetry. And around 30 years later, John Henry Lambert, so this is the one in the Beers-Lambert thing, proposed the first mathematical relationship, the logarithm of the decrease in light intensity. Today we would say it as the inverse of transmittance is equals to the product of the opacity of the medium times its thickness. Okay, so when you're going to look at the transmittance that you have there, okay, they said that it decreased with terms of the light intensity. And then 1850, so this is the one from the Beer's law. Augusto Beer established a relationship between the concentration and optical density. Now we call the optical density as absorbance. So although I think in biology, they still use optical density as the term if they want to measure the microorganism culture. Okay, and this leads to the current Beer-Lambert's law. So if you're going to look at this, we're not going to solve problem today so that hindi agad kayo ma-shock. So if you're going to pass through, okay, the energy here, you pass through this glass, so the amount that what we call coming out is less. So every molecular species is capable of absorbing its own characteristic frequencies of electromagnetic radiation. And this process transfer energy to the molecule and results in a decrease in the intensity of the incident EMR. So the P coming in and the P going out. And they said the absorption of the radiation thus attenuates the beam in accordance with the absorption law. So the way they simplify this one here is just the concept of this what we call transmittance. So transmittance is just equals to the power that comes out over the power that comes in, the light, okay, that comes out over the lights that come. And you can also express it with what we call percent transmittance. And percent transmittance you have here is just the P that comes out over the initial P that comes in times 100. And if you're going to look at this, T has a range of what? 0 to 1. So the percentage T has a range of 0 to 100. And if you're going to relate your absorbance to transmittance, the absorbance is just the negative log of transmittance, or the negative log of percent transmittance over 100. And this is equals to 2 minus negative log of T 100. So yun yung basis nila. Okay? In terms of what we call the Beer's law. In some book, they just call it the Beer's law. And I would suggest try to look at this exercise that that is given here in this link. Now, if you're going to look at this Beer's law, okay, it can be Beer's-Lambert law, Lambert-Beer's law, or Lambert-Beer-Boger's law. Okay, so usually what it tells us, the relative amount of a certain wavelength of light absorbed, A, that passes through the sample is dependent to, I don't know. In my undergrad years, we just say big A is equals to ABC. Okay, this one that you have here, the molar absorptivity, is usually a constant for a particular chemical or compound. Now, the path length that you have there is usually what? Anyone? What's usually the value of your path length? Usually they use the 1 centimeter. Okay. And then the amount of the absorbing chemicals in the sample, that is the analyte concentration. So if you're going to look at this, you could say the big A there is directly dependent on the C. Because the molar absorptivity that you have there, usually that is your slope. Okay, if you're going to do some sort of a calibration or How do you say that? So you have here what? Concentration. And then you have here the absorbance. So if you're going to look at here, and since you know, if you have it, this is usually what? 1 centimeter. So your A is only really dependent on the C. And this one is your slope. So that's the basis that they have here for this so-called Beer's law. And it's really useful until today. That's the reason why even if you have Spectronic 20, you can do quantitative analysis. All you need to do is put a set of standard, okay, or standard solutions of different concentration. So if you're going to look at the Beer's law, you can have absorbance equals to E, molar absorptivity times path length times the concentration, or as I've told you, ABC. And A is just equals to the negative log of T. Okay? And if you're going to look at the Beer's law, it allows the compounds to be quantified by their ability to absorb light and relates directly to concentration. Now, what's the problem with what we call the Beer's law? You cannot use the Beer's law infinitely. So I'm going to what we call jump on some of the problem. There's always what we call a limitations on the Beer's law. Okay. Although we could say it's used largely for quantitative analysis, under certain condition, okay, Beer's law only considers a fraction of absorbed light and hence can only be applied on certain conditions. Because sometimes if you look at some of the calibration curve that you have, there will come a time that at a certain concentration, the relationship between the absorbance and the concentration is not linear anymore. And in that case, you have to limit your Beer's law. Okay, so Beer's law is only applicable in relatively low analyte concentration. Why? What happened when it's already the concentration is already too high? Okay, so usually at high concentration, usually around 0.01 molar, the charge distribution effects occur, causing electrostatic interaction between absorbing species. So masyado na silang concentrated. Okay? And what happened there, because they're so concentrated, the term that they have in some paper, the crowding of these molecules results in this electrostatic interaction. Okay? And what happened there, it will affect the absorbance. In terms of fluorescence, they call it quenching. So too much concentration there of your compound of interest quench already the signal that you have. So the distances between the molecules or ions are diminished to the point where each particle affects the charge distribution of its neighbor. So you can see a deviation here. Okay. If changes in concentration causes significant changes in the relative index, which influence your absorptivity. So may limit usually yung Beer's law. And you also have to take into consideration on the so-called chemical deviation. Okay. So at higher concentration, most likely, or we could say when we're talking about chemical deviation, so this happens when your analyte dissociates, associates, or react with the solvent to produce a product with different absorption spectrum than the analyte. So for instance, this one, the indicators. So you have to make sure you're going to use consistently the same pH. Okay. Now, the principle of your indicator is at different forms or at different pH, they have different forms. And on that different forms, they can exhibit different color. as the one that you see here. Okay. Another thing that we can look on the limitations, so we go first on the principles, maybe next meeting we can do with the problem solving, is the so-called instrumental deviation due to the polychromatic radiation. Okay, so what happened here? So since all instrument has this finite band pass, so a range of wavelengths are sent through the sample. And unfortunately, okay, the molar absorptivity can be different for each wavelength. So if you have this band pass here, this band pass here, so this band pass can give you this one, which is a straight line, but the other band pass will show you a line where it can deviate, okay, from not being linear. So that's another what we call deviation. And then we can also take into consideration here the presence of this stray radiation. Okay, so what happened as the analyte concentration increases, the intensity of light exiting the cell decreases. Kasi masyado na siyang maraming analyte doon. So yung amount na lumalabas ay nagdi-decrease. And what happened when stray light is present, the absorbance observed, which is the absorbance apparent, is the sum of the real and the stray absorbance. So there's already what we call an error that you have there. Okay, there's a contribution from the stray absorbance. And this would result in nonlinear absorption. And the other thing that you can take into consideration on the limitations of the Beer's law is the so-called mismatched cells. Okay, if the cells holding the analyte and the blank solutions are not of equal path length and equivalent in optical characteristic, an intercept K will occur in the calibration. I don't know if you know it, but there are what we call cubette whose path length is less or more than 1 centimeter. So as much as possible, when you do the analysis, you're going to use consistent path length. Okay? Meron pa nga ano I'm not sure, but there are what we call the macro and semi-micro cubette. So you have a cubette here, and then you have like a wider. So I always ask my student, if you're going to use it this position, I want you to use the same position all throughout the analysis. Hindi yung in the next one, pag ganito yung gagamitin niya. Because if you have that white thing here, so the path length here, okay, mas ito lang yung nakikita niya kaysa doon sa side na if you're going to look at this, everything is, we could say, 1 centimeter. Okay, so you have to be what we call consistent in using the same path length. So you can avoid it by using carefully matched cells, or you could say a linear regression procedure, calculate for the slope and the y-intercept, or you can just use one cell of cubette and keep it in the same position. So yun yung sabi ko sa inyo, if you're using the micro or semi-micro, what we call cell. Now, the way that you solve this limitation is the Beer's law is as much as possible when you do a calibration curve, it should be linear, and the absorbance of your sample is within the calibration curve. So what do you do if the absorbance of your sample is so high? Ano yung practical solution na gagawin nyo? Anyone? So when your sample reading is so high, okay, the practical solution for you to do is not to extrapolate, but to dilute your sample. Extrapolation is really a big no-no. Okay, because sometimes you should extrapolate, and then if you're going to compare when you dilute it, the reading that you have when you extrapolate is even lower compare if you dilute it and then you multiply it with the dilution factor that you have. So I think we will end with this one, and then I'm going to start putting the other what we call module by tomorrow night. Okay, but I'm going to ask you to watch some other video that is related to spectroscopy to let you understand how useful this can be. So question. Question? Hi, ma'am.
And then meron lang akong mga additional
Sige po,
doon
sige,
sa
ma'am.
doon sa instrumentation. Kung yung unit nyo ay UV visible recording spectrophotometer, bali meron kayong dalawang lamp or light source. Yung isa is the deuterium and the other one is the tungsten. So yung deuterium, ito yung light source sa UV region, and then the tungsten, ito yung light source sa visible region. So for example, scan kayo ng wavelength from UV to visible. So if you put on the equipment, so on yung deuterium kasi nandun kayo sa UV range. And then mapapansin nyo na as you go to the visible, pagdating nyo ng 330 nanometer, merong click, nagagano. So di nag-change, nag-off si deuterium, tapos nag-on naman si tungsten. So meron ng mga na recording spectrophotometer na merong ganong klaseng provision to yung nagsi-shift ng light source from visible to UV and then UV to visible. Yun. Tapos kanina kasi nag-chat si Kristen, sabi niya yung sa dilution. So it's important that you do not dilute the reacted solution, but you dilute from the sample.
Yun po.
Okay, so yung sample lang i-dilute nyo, and then have it the diluted sample, have it react with the coloring reagent, and then you read. Hindi nyo i-dilute yung reacted na na-colored. Okay, so maling-mali yun katulad ng pagkaka-explain. So you dilute from the start, the sample at the start, hindi yung reacted na colored sample na. Yun. So yun lang sir. Yung aking
Yung ibang part kasi po ma'am na it will be explained. I think the next module is the optical instrument parts. So doon maano natin yung light source like tungsten and the deuterium lamp, and they also have some explanation there about laser. That's what we call the source, because usually the common thing that you have as much as possible is a broadband. You seldom see use this single wavelength unless maybe not in UVBs but in other, we could say, application. So question.
So dapat children mahasa kayo sa UVV spectrophotometry kasi ito yung pinaka-common. Ito isa sa mga common equipment na nasa lab. So if you're going to after you graduate and you take the board and then magwo-work na kayo, whether you are in a research lab or in a QC lab or in a service lab, so you will really encounter UVV spectrophotometer, and talagang mag-handle kayo nito. Kaya ngayon pa lang na nile-lecture ni Sir Elmer, kabisaduhin nyo na yung instrumentation and then yung operation, siguro konting troubleshooting katulad nung sinasabi niya kanina, and yung principle ng mga bawat methods.
And this is cheaper than chromatography. Sabi nga nila, after daw nung balance, ito yung makikita mong instrument sa lab. I mean,
Mm-mm.
you will not be able to see chromatography unless siguro TLC or paper chrome. But most likely you will see either yung electrochemistry, which is pH meter, and this what we call spectroscopy. So usually spectronic 20. Even now, I think this week I have an experiment wherein we use spectronic 20. Pinatapon na nga nung yung head nung ano namin sa lab, yung mga spectronic 20. Sabi ko nga, ba't mo tinapon? Sabi ko sa iyo, wag mong itapon at gagawa ko ng paraan. Because we have, I think, 5 spectronic 20, tapos pinaano lang niya, hindi, bago pa lang ako nung time na yun. Ang ano yung nag-upgrade kasi sila dito. Kaya I told you, I asked them, can you, yung UV Beckman, ma'am, meron sa ASL dyan. So I asked them, no, don't throw it because I want the student to show the difference doon sa signal na nakukuha doon tsaka doon sa modern. Para at least makita nila yung difference. Natatawa pa kami kasi alam niyo yung floppy disk na parang 3D nung save. Tawa yung estudyante ko kasi yun yung inaano namin, ginagamit. This is an instrumental analysis course. Tapos yung, I think, yung HPLC namin, I don't know if you know Clippy, yung parang nag-aano kapag nagma-Microsoft Office ka, may lalabas doon na parang clip na nagsasabi kasi, oh, this is old. But that is trying to what we call making them familiar doon sa old na ano. Kasi usually, kapag na-train ka doon sa old, when you handle a new one, it's just so easy. Kaysa doon na-train ka sa new, tapos yung lab, yung instrument mo i-old, parang ano to?
Oo nga.
So what we do is a combination of an old one and a new one. So nung dumating ako, usually kinokondem lahat nila yung mga luma. Sabi ko, no, I need that in my instrumental class. So usually I have this old one and a new version of this thing. So usually ayaw nila yung old kasi nga mabaga. But I can tell you that in all labs there in the Philippines na kakilala ko in DOST, they always have these UVBs, and I can tell you it's a very useful quantitative analysis. Makuha mo lang yung reaction. All you need to do is like a coloring material or coloring dye. And usually that's the principle that they use when you do this biological test, yung mga urinalysis ninyo, and try to determine like creatinine or other stuff. They develop it, okay, by using this reaction of your sample with a particular dye, and then makakita sila ng colored, and ipapatent na nila yun. So that's the what we call essence of this UVBs, visible absorption spectroscopy. So it's really useful. Even whenever I do analysis, I still want to do it because the samples that I utilize, like the B products and the T products, I said, by just looking at the UVBs, you can see that there's a difference in the structure of your sample.
Okay.
Yeah.
Ayun.
So wala kayong quiz for now.
So tatanong ko lang yung mga students ko sa section ko kung natanggap nyo ba yung yung material, yung spectrophotometry, na yung spectroscopy PowerPoint, natanggap nyo ba? Carl?
Parang wala pa po yata.
So ito, tingnan nyo. So
meron ba sila nung link nitong Google Drive?
Dapat po, kasi ganito rin yung ginawa ko sa B2 eh. So if you're going to look at this, so the way that I do it, you go to the Google Drive, tapos hanapin nyo yung classroom nyo doon. So as you could see here, so ito yung mga classroom ko. So sa B2 ko, nandoon yung Chem 137 materials. So if I go back there, in the 137V, I also posted this one there. So try to see now kung kaya nyong i-access yun.
So meron na silang link doon sa Google Drive?
Dapat po. Kasi ano sila doon eh, may access sila dyan sa drive na to. Kasi doon ko po nilagay yung folder.
Okay.
Kasi kayo po naglagay nitong iba dito eh.
Oo.
Kita nyo yung mga
Okay.
nilagay yung ano yung separate na PDF.
Oo nga.
So
Oo.
kung meron
Nakita
silang
na po,
access
ma'am.
dyan,
Nakita nyo na?
ma-access
Okay.
din po nila yan.
Ako po, nakita ko.
Okay, sige.
So I think if we're going to look, we have more or less 2 months, but i-extend kasi sa yung ano ninyo, yung final exam ninyo until New Year eh. And we're hoping we can catch up. Okay? So question. Ano ata question? Tanong? Before we call it a day, to tell you frankly, behind na po kami. Nag-daylight na kami, so alas 12 pa lang.
Okay.
We
Oo nga
usually,
pala, summer. Ano
Opo.
pa? Ano na, going to
Fall.
autumn na, no?
Opo, fall back kami.
Fall na.
So I'm going
Okay.
to post the recording hopefully by tomorrow kasi